Okay. Hi, everybody. Today lecture is about Python node which exists in LabVIEW and is used to interface between LabVIEW software and Python software. To show you where it exists and how to call it to the block diagram, we open a new VI like this. This is the block diagram. Simply right-click on the block diagram, and here you will find connectivity group, and within this palette you have Python node group. In Python node group you have, as you see, 6 simple VIs. One of them is this one, which is called the Python node. If you click it and put it on the front panel, it will be here for use, ready for use. In order to work with the Python node, usually at least we need also to work with other two simple VIs. One of them is Open Python Session. This is the VI here. And the other one is also closes connectivity. It also closes the session here, close Python session. So this is, as you see, the close Python session. This is the node itself, Python node, and this is the node which initiates the work and opens the session. The output of the open Python session here, the session output is connected with the input session N for Python node, and the same thing happens with the following VI. We connect the identifier with this one here, and this is the connection as usually, which shows if there is an error somewhere occurring in the system. So these are the main components which are to be used when realizing interface between Python and between LabVIEW. Few words about this is necessary to mention that LabVIEW is well known as really a very strong and a very adequate environment for engineering work. Since its appearance, it was used for data acquisition, and it was a marvelous interface which connects directly with the external environment to the computer, and by means of the software which is installed in the computer, you can connect between the real process to the DAC board, which is installed in the computer or beside the computer. And inside the computer, you carry out, by using LabVIEW, the required signal processing and even conditioning. You convert the analog signal to a digital, you carry out multiplexing when necessary, you carry out multiplication of the signal, and at the end you digitize the signal and input it to the computer. Inside the computer, there we can make use, of course, of many VIs of the LabVIEW to carry out different operations like differentiation or integration or filtering, also digital filtering, or any other action like PID control action or fuzzy logic action, and so on. So LabVIEW is very famous and successfully used as an engineering language which connects between the processes and the computer, into the computer and outside from the computer. Of course, the signal out of the computer has a small current and a fixed level, usually about 5 volt. And in order to connect with the process, you need externally to furnish a power interface between the computer and the real external environment. On the other side, really, we can say that Python excels LabVIEW in the area of machine learning because it deals with huge numbers, huge data numbers, items, and it has really a very large number of additional libraries which are built on the basics of Python. This includes the SciPy library, for example, Pandas library, Scikit library, sklearn or SciPy library, or Matplotlib library, and many, many others libraries, which makes working with the Python is an easy job, especially for regression and classification and clustering activities. So it seems now it's clear that the best thing we do here is to join between these two marvelous environments and to join them together so that we can supply the data to LabVIEW, from LabVIEW to Python through this Python node. And inside Python, we carry out the regression and classification tasks. And at the end of that, we pass back from the Python to LabVIEW the results to display it on the front panel. This is really an important and an excellent work which could be realized by using this node. Today, I shall go with you through several simple examples for beginners. In the next lecture, I shall go also deeper and illustrate with you more interesting examples where we work with the machine learning tasks. So let me begin illustrating to you very simple examples so that you can get an idea about the mechanism of data flow from the Python node to LabVIEW and from LabVIEW to the Python. Yes. So suppose we have this short piece of code which is used to carry out addition between two variables. One of them the variable x and the other one the variable y, and we want to find its total. But we want the addition process to be done by Python, and the results will be displayed in LabVIEW. To carry out this job in Python, we need to import NumPy library as NP. We have always to work with functions when making interface between Python and LabVIEW. So here we create a function, we call it addition, and the parameters or variables here are x and y. And we want from this function to return the sum of x and y. In order to do that, we have to go now to LabVIEW to establish the code which is required there, to furnish the input of the Python node with the values of x and y, so as to get the result from Python, which is x plus y. So I go to LabVIEW and I call a simple program I have created for this purpose. I have called it Python node add two doubles. So this is the front panel of the program in LabVIEW, and this is the block diagram. Let us try to explain to you the basic elements which are included here and how they work and synchronize their work with the piece of code which I showed you in Python. So at first I have put on the block diagram the Python node. I have brought it from the library of LabVIEW, and also I have put here the Python, open Python session and close Python session. This is very essential. Now, this node requires always the name of the function which you create in Python. Remember, I have called it addition. If you go there, here it is addition. This is the function defined in Python, and this is the name of the function. So the name now is given and written as an input to Python node. This is a string called addition. The other important thing, when you create the function in LabVIEW, this code, all the code must be saved in the computer, maybe in the documents folder, or maybe anywhere where it is easy for you. But it should be saved there with an extension .py as a Python file. I am working with Jupyter Notebook. To save this in Jupyter Notebook, the easiest way, I think, is to copy and paste this code in the notepad, and from there you save it wherever you want. So I mark it, or I select the code, then I copy the code and paste it here in the notepad. Now here is the code again. From here I go to the file and save it as, and give it a name here with an extension .py, and it will be saved. Here it is, for example, it should be saved with Python folder, or it could be saved with the documents or anywhere you want. So this is a requirement. A first requirement to work with is to save the code which you have created in Python with a given function or more than one function, and to save it as a Python file. So when I go to the front panel again, And now at this point here, you see the module path. The module path here represents the path of the file which I have already saved. This file is saved at the documents, and its name, as you see, addition of x and y dot python. Addition of x and y. So if I go to the documents, it should be there. If I go to the documents, let me go and show you. This is the PC. This is the documents. And now, if we go there, addition x and y dot py. Here, this is a number of files with the extension py. Here is our function addition of x and y dot py. So it exists as I wanted. Suppose you have forgotten the file and content, or you do not want to go back to Python to have a look at it or to make something with it, you can here right-click it directly and open also it with maybe Notepad, or you can open it, for example, Visual Studio Code. If I press the Visual Studio Code, I shall also have an idea to see exactly the same program which I have already saved. Here it is again. Okay. I don't want to change anything, but I have just wanted to show you how you can play with it. And I have shown you where it exists exactly as I have already saved it in the documents. So this file now already is saved in the documents as required. And I have shown you again, I show you again how this is the path, and the last element of the path contains the name of the Python file. So it is there. These are two important requirements. Here at the open session, you are required to define the version of Python which you are going to work with. Here it is a very, very important and crucial thing to know that the bits of the Python version here must be 32 if you are going to work with LabVIEW with 32 bits. If you are going to work with LabVIEW 64 bits, so this version of Python must be 64 bits. This is essential and very important. But because there are many versions in Python, and they are updated every year more than one time, Python, beginning from the version number 10, makes or generates the code with 64 bits. So in order to be able to work correctly with this issue, the LabVIEW issued a table which shows compatibility between the versions, different versions of Python and different versions of LabVIEW. Here, I found that the version 3.6 is from the same beginning, was generated by Python with 64 bits. So, and LabVIEW must be, in this case, 64 bits. I have installed LabVIEW here with 64 bits. So now there is no contrast or mode function will not happen because they are synchronized correctly. What else here? The node to work, of course, it expects an inputs and outputs. The output which is expected here may be more than one item. It could expect an item like a double precision numeric value, and as it's shown here it is shown that the output is a double precision numeric value, and the output may contain a value also as an array or a list. This also could be. So what it requires throughout the input here to show the type of the data which is going to be generated as the output. I know in advance that I am making a sum of values and the result will be a value, a numeric value. So I create here at the input an empty element with a zero value, but it is numeric, as you see, and the output also will be numeric. What else here? We need to import the value of the first variable. I call it x. It is also here created at the front panel. It should be at the, sorry, it should be at the front panel. Here, x is equal to 5. This is a value of x, and y is equal to 8, for example. This is also a numeric input, and it is not an array, and this is a numeric input. So both of them now are fed. X is fed. This is the terminal of the value which is at the front panel, and this is the terminal of the value which is at the front panel. Both of them are fed to the left side of the Python node, and that's it. Now, if I run the program, the output which is there, sorry, this output here, which will be returned by the function, will be the sum of x and y. So if I go back to LabVIEW, to the front panel, I shall see a terminal here, x and y, and here will be the result. Now, if I run the program, 5 plus 8 equals 13. If I change the input, for example, plus 45, for example, and 5, this will be 50. If I run the program again, now it will give you 50. Note here also that the state of the program is shown through the error track here, which connects between the different elements. This is at the input side control, and this is the indicator at the outside. Both of them show, let me go out from here. Both of them show that this thick green one and this thick green one, which means that the program is normal. There is no contrasts, or there is no problems or mismatch between LabVIEW and between the Python program. Run it again. I can change the value from 5, for example, to 56, and 45, it will be 91 or 101 again. So the program is working nice. So again, we have to begin with the problem in Python. We have to write the program in Python so that it contains a function. And this function must have a name, and it must include the variables which are going to be used by Python. The name of the function in Python is defined as a string at the input of the Python node. After the creation of that code in Python, it must be saved as a Python file in the documents or in any other appropriate place. Then we have to define the type of the output and give a similar input empty, but this is just a requirement by LabVIEW. After that, you can input the variable X, the variable Y, and you will get at the output what is expected to be. I hope that I have explained it simply and easily, but when going through other examples now, I think you shall feel more comfortable and you will understand it much better. Okay, so let us go again to LabVIEW and see another program. I am demonstrating with you a program where we multiply two matrices. Import NumPy as NP. Matrix number 1 is given as a two-dimensional array, NP array 1, 2, 3, 4. These are two lines, two columns, and the other matrix of the same size, NP.array of 5, 6, 7, 8. So I have created two matrices in Python, and I want to multiply them. For this purpose, I shall use NumPy and call from NumPy matmul. This is mathematical matrices multiply two matrices together. So from NumPy, I call the function matmul between two brackets, and I pass to this function the variables matrix 1 and matrix 2. And this result will be saved in a variable called result. And now I ask the program to print this result. As usual, if I run this program, as you see, I shall get the answer which is shown downwards, 19, 22, 43, 50. This program, as you see, contains no function. This is a normal Python function. As usually we do, it is programmed to work as a Python function, and this is the results I wanted to show you, just to show you how it works and what are the expected results for these values. Okay, now let us go and try to multiply them by using Python node. So this program must be somehow modified, and it must include a function with a name, and this function will include matrix 1 and matrix 2 as variables. This is done here. Now I have created or defined a new function. I called it multiple or multiplication. The variables are matrix 1 and matrix 2. And I want to use NumPy mul function. So again, I passed in Python matrix 1 and matrix 2 as arguments, and the result now will be returned. Look at the difference between this program, which was made for Python use only, and this now is modified to work with it by using the Python node. Here I have given the numeric values, elements of the matrices. Here I have just given the name of the matrix, but the values of this matrix and this matrix will be given from the Python front panel. Let us go there and see what we have. And remember these answers: 19, 22, 43, 50. Okay, we go there again. We open the file which I have saved for this purpose. It is 21. Now this is our program. So again, I created Python node. I have created the open session, and I have closed the session. The name of the function which was created is multiplication. It is now fixed here as a string. And this now is the path of the function which I have created in Python, and I have saved it in Python folder. If you go to Python folder, we shall see this file with extension Python. Now I have created matrix 1, 1, 2, 3, 4, and created matrix 2, 5, 6, 7, 8. These two matrices will have terminals here. This is the terminal of matrix 1. This is the terminal of matrix 2. This is a two-dimensional matrix. This is a two-dimensional matrix. So really, I have at the output here 2 lines, and this is the input, and this is the other input. The result of multiplication is expected to be also a two-dimensional. So here I have created an output indicator. I called it matrix 1 multiplied by matrix 2. It is two-dimensional. And here at the input, I have to create an empty two-dimensional array. I have again fixed the number of the version of Python. Now everything is okay here. Here, if you want to show the path which refers to the position of the Python execution file, you can do it, but it is, I have done it, but it is not a must. The program works without this. This is not an essential requirement. Now, if you go back and run the program, we shall see that the result is exactly as the same which we have got in the Python. And as you see, these two ticks show that the program is okay. If I change any value here, the result will be changed here. Suppose instead of multiplying by 2, I have written 89, for example. Now, if I run the program, of course, the results now are changing, and they are different than those before. But the output matrix is still to be a two-dimensional. Okay, let us go back, exit. Let us go and illustrate with you another example. Here I am trying to work with a 3-element, 3 rows, 3 columns matrices. The program here is written only for Python to show you that the result will be also a two-dimensional matrices with the first row 1, 2, 3, 4, 5, 6, 7, 8, 9 as it is here. And this is the second matrix, which is multiplied by the first one. Now, if we go to LabVIEW and see how it is realized. Oh, it seems to me that I have opened LabVIEW version 21. This is not suitable to work with because it has 32 bits. So I shall now quit out of it and return back to LabVIEW version 25, which is with 64 bits. So I quit away of it. I don't need it. I go to LabVIEW again. Here, this is version 2025, which has 64 bits, compatible with the bits of the Python 3.6. So now we are here. I can open the file which I wanted to demonstrate with you. It is number 22. Here now I have created 3 elements, 3 rows by 3 columns. First matrix called A, the second matrix called B. This is the output which I expect to receive, which will be also the same 2-dimensional array. And this dimension array, which was created in Python, was written or was saved in the documents with a name, mat, matrices multiply dot py. So if I go to the block diagram, it will be very similar to the one which we have created before. This is the node. This is the Python session opening, closing, and the input here 2-dimensional array, which is B, and the input here 2-dimensional array or matrix, which is A. And this is the model of the expected output data type, which is also an array, 2-dimensional. Everything is normal. Now, if I run it, of course, it will give the same results. 1, 2, 3, 4, 5, 6, 7, and so on. If you change any value in A or in B, of course, the result will be different. Let us change, for example, number 8 here to be like this, 6, 5, for example. Now we shall have a different value as the output here. Now it is given, but here it is instead of 6, now it is 6, and 5, 4, the same. But here it is changed. It is now 65, the output. Here, the matrix was given as 1, 1, 1, as you see. So I hope that this is also easy, understandable by you, and let us move forward and discuss with you more interesting programs. This is another program of this kind, but it is to demonstrate how we can multiply a matrix by a vector. The expected value will be a vector. In Python, I have done this in 2 different ways. The first way, by using numpy ... function as multiplier, and sometimes also you can use at. This is the at symbol. Now, let us go through it quickly. So I have created an array, I called it C, 2-dimensional, with, as you see, 2 columns and 3 rows. And here is a vector. And now I have multiplied them, and the result will be printed, and it is 8, 18, 28. If I select it and run the program, it will give exactly the same way, the same number as you have seen. I have so this cell, I want to show the first cell. So also the first cell gives 8, 18, 28, and this one gives 8, 18, 28, which I wanted to show that they give the same answer, but both of them are organized to be as completely Python codes. These are not made to make an interface between Python and LabVIEW, because as you see, I have passed the numeric values and I've created real matrices. So there is nothing about interfacing between Python and LabVIEW. If I want now to carry out the same job, to multiply a matrix with the vector, so I have to create a function. So again, I imported NumPy as NP. I've created or defined a function. I called it matrices vector multiply, for example. And the variables are C and V. C represents the matrix, V represents the vector. And what I expect to return, NumPy matrices multiplying C and V. Of course, if I run this program here, it will give me no result because there is no numbers here. Nothing you get here. But this program now will be saved in the computer somewhere where it is adequate for you, and the path of this code will be given or fixed to the Python node. So if you go to the Python node now, continue with LabVIEW. Now we will open the node, sorry, the block diagram, multiply matrix by a vector. This is number 3. So if I open it now, this is number 3. Okay. An error occurred, loading so and so by. It seems that I am working with this LabVIEW version. Again, I have made the same fault. So, okay, I have to go out of this LabVIEW to LabVIEW version 2025, and work from there. Here it is. I am sorry, it happens. Directly, the program has detected that this version is not suitable for this program. Now I open it and go to number 3. Now it will open. So this is my program here. This is the front panel, and this is the block diagram. The block diagram components exactly are the same and doesn't change, but the content changes. So here the name of the function, mat vector matrix vector multiplying. Here the address path where I saved the Python code. And here at the input now, I expect as the output to have a vector here. No, here it is an array, but it is one-dimensional array. So I gave here at the input a one-dimensional array. And C and V, this is a one-dimensional array vector, and the matrix is called a two-dimensional array. So this matrix now is the look, this is one dimension, this is the other dimension. This represents the matrix 1, 2, 3, 4. This is 2 columns and 3 rows. And the vector here is this column. It is one-dimensional and it contains, for example, 2 and 3 values. Now we want to multiply C and V, and we get as the output the output, which is C2 here, called C2. It is here. This is the output which we are expecting to have. If I run the program now, I shall have these values because I didn't change anything here. And the returned value, as I said, it must be, yes, here, no problem, it is okay. Okay, now let us also go and look at another example. Let us try to change Celsius degrees to Fahrenheit degrees. So I have created a function, define Celsius to Fahrenheit. This is the name of the function. And the contents is one variable, it is called Celsius. So I have to give as an input a value which represents the Celsius degrees. And now I have to carry out or implement the following law. Celsius, this is the variable, Celsius, multiplied by 9 divided by 5, plus 32. This gives a value which is saved in a variable called Fahrenheit. So now Fahrenheit, this one will give the output. I have put here in return, I want to read Fahrenheit, so Fahrenheit value will be passed to LabVIEW. If you go there, again, this is number 4. You will see here that I have an input here as a slider so that I can change the value of Celsius value as I want between the range 0 and 10. Of course, I can make it between the range 0 and 100, for example. It depends as you want, or between the range minus, for example, no, minus, for example, 67 and 100. This is the value. It depends what you want. So this is the value of the Celsius degree. It is now here, must be passed to the front, to the block diagram as a terminal. Here it is. It is the same terminal there. And now, from here, this is the input. We have only one input. And this is just to show that I will have an output as a numeric value. This is the Celsius value. I have to put it downwards a little bit. Yes, the slide represents a Celsius value. And the path here shows where it is saved. It is saved in a file called Celsius to Fahrenheit Python in documents. So everything is prepared as should be. And now if I run the program here and give at the input a value, I shall get at the output the corresponding value in Fahrenheit. So, for example, here the value is about 0, as I see. If you want to see it exactly, you can click here and visible items and digital display. Now, this digital display will show you exactly the value which is there. It is 0. If I run here the program now and the input is 0 Celsius, it will be 32 in Fahrenheit because we know this from the physics. Now, if I move this one from 0 to, for example, let me say, I can make it here better. I can, now it is about 10. If it is 10, it will be about 10, about 25 here, about 50. So if I run it here, now it will not be 50, 50 more, a little bit more, because here it is 10.9, here 51.7, so and so. If you want to put it here 10 exactly, you can do that, of course. And at the output now you will get 50, exactly 50. If the temperature in Celsius is minus 40, for example, so in Fahrenheit now it is about minus 40, and so on. So the program works fine. Don't save anything. It is okay. Well, I think it is now sufficient for you. I have explained to you the virtue of using this programmable interface between Python and between LabVIEW in order to add together the advantages of LabVIEW as a very excellent interface for measurement and display, and to join this with the excellent facilities of Python for working with the big data and making use of the tens of different libraries which are built on basics of Python to realize classification problems and clustering problems and also regression. In the coming lecture, I shall concentrate on using or on realizing regression activities by using the Python node. Until then, I wish you the best. Happy day for you, and goodbye.